Welcome to Teacher Course class. This class is being designed to assist NATED engineering students from TVET colleges. Today we'll be focusing on Engineering Science N3, and our topic is moments. Let us divide moments into 3 units. That means today we'll be working on Unit 1. Unit 1 will cover the following objectives: force, moment of a force, law of moments, and examples. A beam is a structural element, whereby in this case certain forces are exerted as shown in the sketch. A beam will typically consist of point loads and reactions. These are types of forces exerted on the beam. On this example, you will notice some new members on the beam: direction and fulcrum. A fulcrum on the beam is introduced when we want to rotate a beam, either clockwise or anti-clockwise. Each force, depending on the position of the fulcrum, will rotate on its respective direction. Let us consider moments at our right-hand side reaction. This means that our fulcrum will now replace the right-hand side reaction and the beam will start rotating at that point. Each force will have to be moved to the fulcrum with respect to its position, as illustrated on the sketch. With this method, we'll then be able to determine the left-hand side reaction. And if we're looking to determine the right-hand side reaction, we will use the same method but now moving all the forces to the fulcrum, which is now on our left-hand side. Moment of a force is the product of the force and the perpendicular distance from the point of application to the turning point. Let us look at the key words: point of application and the turning point. Point of application is the position of the force where the turning point is at the fulcrum. Previously we mentioned that a force will have to move to the fulcrum. Well, this force will move to the fulcrum with its perpendicular distance. On this example, if the force shown on the sketch pushes down the beam will start rotating in a clockwise direction. The law of moments states that, if a system of forces is in equilibrium, the sum of clockwise moments about any point is equal to the sum of the anti-clockwise moments about the same point. Because we need to know if the system is in equilibrium or balanced, we therefore need to have forces pointing down and forces pointing up on the same beam. Equating these nature of forces, we will then be able to determine if the system is balanced or not. For the system to be balanced, the sum of upwards forces must equal the sum of downwards forces. Let us analyze the given example and see if there's anything weird about the problem. 120 newtons force is right on top of left-hand side reaction, and the right-hand side reaction is 3 meters from the right-hand side. These are important to point out before you start doing your calculations. On this example we need to calculate both reactions. But before we start, let us take moments about the left-hand side reaction. This means we'll have to substitute left-hand side reaction with the fulcrum. Doing this, you will notice that the very same 120 newtons force is now on top of the fulcrum. Since this is the case, the perpendicular distance of this force is now 0. Therefore at this point we do not have a moment of this force. Also note that all forces are represented by different colors. This is to help you understand each force's perpendicular distance to the fulcrum. Let us start with the 200 newtons force, which is closer to the fulcrum, to determine its moment and direction. This force's perpendicular distance is 2 meters to the fulcrum, and if this force is pushed downwards, the beam will rotate in a clockwise direction. Let's do the same with 180 newtons force, which is the second closest force to the fulcrum. Its perpendicular distance is 5 meters to the fulcrum, and if this force is pushed downwards, the beam will rotate in a clockwise direction. Look at the second last force, which is the reaction. Its perpendicular distance is 7 meters to the fulcrum, and when this force is to be pushed upwards, the beam will rotate in an anti-clockwise direction. The last force is 350 newtons with a perpendicular distance of 10 meters to the fulcrum, and if this force is to be pushed downwards, the beam will rotate in a clockwise direction. To calculate the left-hand side reaction, we will have to replace the right-hand side reaction with the fulcrum. Every time we do our calculations, we'll always consider to start with the forces closest to the fulcrum to determine their respective moments. Let us therefore start with the 350 newtons force, which its perpendicular distance is 3 meters to the fulcrum, and if this force is to be pushed downwards, the beam will rotate in a clockwise direction. 180 newtons force perpendicular distance is 2 meters to the fulcrum, and if this force is pushed downwards, the beam will rotate in an anti-clockwise direction. 200 newtons force perpendicular distance is 5 meters to the fulcrum, and if this force is pushed downwards, the beam will rotate in an anti-clockwise direction. 120 newtons force perpendicular distance is now 7 meters to the fulcrum, and if this force is pushed downwards, the beam will rotate in an anti-clockwise direction. The left-hand side reaction's perpendicular distance is 7 meters to the fulcrum, and if this force is pushed upwards, the beam will rotate in a clockwise direction. You are doing well so far if you manage to understand this example. Now that we have calculated both reactions, what we need to do is to verify if our system is balanced. Therefore, take the sum of downwards forces and compare them with the sum of upwards forces. Remember, for your system to be balanced, upwards forces must always equal to downwards forces. Congratulations, you're now ready for Unit 2. Thank you for watching this video. Don't forget to like and subscribe for Unit 2 and more videos. If you have any questions, feel free to leave your questions on comment section.